Hmm. Okay, this is lecture 23 and it's part 2. So in the part 1 I have just to show you the motivation about the mixed mode simulation, and the last part of part 1, so we have discussed the implementation part. So in general, implementation of passing the netlist would be a little bit difficult. So instead of considering this general parsing capability for netlist file, we assume a specialized case where a register is attached to a terminal. So instead of the general implementation, consider a register called as R sub I, which is attached to the ith terminal. For example, we can think about R cathode or R anode for our cathode and anodes respectively. Then, for example, if we apply 10 volt, then this is just 10 volt. External voltage is 10 volt. However, so say that here we have a certain Ri, and this is our device. Yes, here we have a device and it has a contact called the ice contact. Then following the convention of our terminal current, actually the direction of ice terminal current is coming from external world into the device. Then in this case we have the external voltage which is connected to the voltage source, which is given by this number. Then what will be the actual voltage felt by our device? Since there is a resistor in between them, then we can say that from this Vi external, the provided one, there will be certain voltage reduction. So voltage drop is simply given by II times Ri, because you know Ri is defined on this part. However, between this node and our contact terminal, there is no other way to flow away. So all kinds of Ri is just kept over this path from external voltage source to the internal terminal. So now we can define this quantity as an internal voltage, so as shown here, and just to use this internal voltage instead of the external voltage for our boundary condition. That's it. One note for this implementation is if we just introduce in this way, actually by changing the solution at each Newton iteration, this R sub I, the ith terminal's terminal current can change really rapidly. So if we don't consider this kind of dependence, then it is very difficult to get the converged solution. So for better convergence, for reliable simulation, we have to include the terminal current and internal voltage, internal terminal voltage in our unknown variable vectors. Okay, so therefore, in this system, in this new system, including the terminal resistance, then we have the conventional unknown variables assigned for potential, electron density, and hole. After that, at the end of this vector, we have to include also voltage and current for those terminals in general. So that should be very carefully done. So most difficult part is calculating the dependence of terminal current on internal variables. So however, that was already done in our Jacobian matrix for internal matrix. So it can be done if we just follow step-by-step manner. Okay, so this was the discussion about mixed mode simulation. So what we can get up to now is, although we cannot consider all kinds of complicated structure, but what we can do is, yes, now we have a certain semiconductor device and multi-terminal device, and it has some terminals. So if you do it correctly, then each terminal can have its terminal resistances. So if we have this one, then we can apply certain voltage and another voltage and another voltage directly to this external contact, and after that there will be certain voltage drop across this internal contact terminal. So R1 times I1, R2 times I2, R3 times I3. There will be certain voltage drop across it, and across it, and internal voltages will be differed from these external ones. Okay, that was the result of our discussion in this part. Okay, now let's go to the transient device simulation, the main topic of our lecture. So now we believe that, okay, now even we can consider the resistances attached to our terminals, then how can we consider this transient simulation for circuit? So simply speaking, compared with the steady-state solution, or the strategy for steady-state simulation, the only difference in the internal equation comes from continuity equation. It is because the Poisson equation doesn't have any time-dependent term. Since there is no time derivative term, so calculation of a potential is always instantaneous. So the instantaneous values of our electron density and hole density determines the electrostatic potential. So we don't have to change Poisson equation. But instead of that, continuity equation has its own time derivative operator. So we must consider these two terms. Then how can you consider these two terms? So let's just consider 1D space, and for a certain central load x sub I, as usual we just integrate the continuity equation. This is for electron continuity equation, but that is the same for our whole continuity equation too. So time derivative term is simply multiplied by delta x, because you know this is just defined on x sub I, and this becomes the representative value over the control volume, and this control volume is simply given by this one. This is quite similar to that of integration of Poisson equation. Here we have net charge density related terms, and what happens when we just integrate it over certain control volume? We just calculate Q times P at x sub I multiplied by delta x. All of these quantities are treated in the same way. Therefore, also we just multiply delta x here. Then the remaining task is quite easy. So now we just introduce our backward Euler scheme into it. then we can say that here we calculate the difference between the present value of electron density at a certain node and the past value of electron density at the same node and taking the difference. Of course, it is originated from backward Euler method, and if you consider higher order method like Geer's second order method, then you have to consider other past values, but it can be easily extended without much difficulty. So now we have this additional factor. But please note that in order to implement this one, we must memorize the past value of electron density. Well, so it is not that difficult because actually the past value of your electron density was the present value of your previous iterations or previous time step. So you can just make a separate vector containing this n past, then that is used to calculate backward Euler time derivative term. Okay, then how about the Jacobian? Uh, Please note that this past value is no longer an unknown variable. Previously, it was an unknown variable. However, since already that time has passed and this is now just a given number, so we don't have to consider the time partial derivative with respect to this number. So, simply speaking, it does not contribute to the Jacobian matrix. The only change in the Jacobian matrix from the electron continuity equation is simply comes from this component. And when we take the partial derivatives, then this one goes away, then this number is simply a constant number, minus q times delta x over delta t. So that's it. So you know this contribution is increased when you have delta t goes to 0. When you have a small delta t or small delta t, then the contribution of this time derivatives goes up. And if we go to delta t equal to infinitely large, then actually this term does not contribute much, and it is corresponding to the quasi-stationary or quasi-static case. Okay, and you know that this component is usually assigned to a diagonal component. So always it is good to have this time derivative term. Okay, so up to now I have thought about what we should change when we consider transient simulation internally. So actually that's it. However, in order to calculate the terminal current as a function of time, we must consider additional modification. So please note that this slide does not relate with getting the solution. The solution can be obtained without considering this displacement current. However, if we wanted to calculate the terminal current, then we must consider this displacement current contribution. You know, they are all related with the particle current density and they were used in the DC simulation. But transient case, we have to consider this additional displacement current term. Then how can you calculate this displacement current? Okay, so now we have to say if this is the O node, then of course we can calculate the current densities, the midpoint between these two neighboring components. So this midpoint of an edge is selected, and we have already done for calculation of hole current density and electron current density. So the only remaining term is related with this displacement current vector. Then how can you calculate? Here we have time derivative operator, and now D should be written. However, D can be expressed as epsilon permittivity times electric field. So here we have permittivity. And now we have to calculate the electric field, and electric field is simply given by minus times gradient of electrostatic potential. That is realized here, minus times gradient of electrostatic potential. Of course, here we have a time derivative operator, so it simply means that when we just write down all explicitly, then this term in parentheses can be just written as delta x, delta t, and phi x n minus phi x n minus 1. This is present value minus phi x n, however, calculated at past time points, plus phi x n minus 1, however, evaluated at past time points. Or it looks a little bit complicated, but you can calculate it from your current variable and previous variable, so you can do it. This is a little bit complicated, but I hope that everybody can do that. Without considering this displacement current, you cannot get the current continuity. So please be careful to include it. So I think that that's it for our today's lecture. So although I have quickly covered these two topics like mixed mode simulation, actually not the full mixed mode simulation, but attaching the terminal resistances to terminals, and considering the time derivative term and considering displacement current term. However, actual implementation is quite involved, so you must consider considerable effort to real implementation. So please have your time to extend your code to these two capabilities. So my suggestion is please do this please do this mixed mode capability or a resistor, terminal resistor one first. After that, expand it to the transient cases, because that will give you more applications for your implemented device simulator. Okay, so that's it for today's part 2, and let's have another lecture on this Wednesday. Thank you. Bye.